everyone.
Glad to have you back. So we're going to have our last talk of the meeting, Daniel Gottesman, on spin glasses and computational complexity. Okay, thanks. Of course, the field of quantum information is very much an interdisciplinary field. It has very heavy presence from physics and from computer science, as well as a variety of others. And this talk in particular is going to be phrased as kind of a conversation between physics and computer science, as represented by these two characters here. I imagine you can guess which is physics and which is computer science, but if you can, it doesn't really matter. So, okay. So to start off, let's start with a very basic question that physics might be asking to computer science, which is, what is a computer? After all, that's the basis of your field. Okay? Unfortunately for the physicists, the computer scientists can come up with a number of different answers. So the computer scientist might say, oh, well, there's this Turing machine, and Turing machine has a head, and it moves along the tape. But if you go to talk to a different computer scientist might say, oh, it's a sequence of gates, and each gate will interact some number of bits and get some outputs, and we put these together to make big circuits. And if he goes to talk to a third computer scientist, the third computer scientist might say, oh, well, you can think of a computer as just a cellular automaton that has an update rule on each cell in some lattice, and it only depends on the cells around them. And the physicist, after getting these three totally different answers, might get rather frustrated and demand why the computer scientists can't make up their mind. One of these should be a computer. What about why are we getting all these different answers? But of course, the answer from the computer scientist is that it doesn't really matter. That while they're all different possible ways, and on the surface they seem very different, of implementing a computer or defining a computer, in practice they all give the same answer. In particular, they all give the same set of computable functions. And that's, of course, the deep insight behind the field of computer science. That's why the field of computer science is a field rather than a whole bunch of different fields of Macintosh computer science and PC computer science and Unix computer science, because they all compute the same thing. And more than that, they compute the same thing at roughly the same speed. So what do I mean by roughly the same speed? Well, so for instance, you might say, well, okay, so let's fix one of these architectures. Let's say gates interacting to make circuits. But we'll consider one gate network where things can interact in 3 dimensions. The bits are arranged in some 3-dimensional structure, and bits which are near each other in this 3-dimensional structure can talk to each other directly. Other ones have to talk indirectly. And compare that to one that's arranged in 2 dimensions or 1 dimension. Now, clearly, the 3-dimensional one should be faster, right, because bits are closer together. And occasionally, bits that are far apart will have to talk. But when there's n bits in the computer in 3 dimensions, there'll be a distance at most n to the 1/3 apart, whereas in 1 dimension, there'll be a distance n apart, right? So clearly the 3-dimensional one, in some cases, will be faster than the 1-dimensional one. And so the computer scientist says, yes, sure, that's true. But that's not a really big difference, right? That's a difference between n and n to the 1/3. That's only a polynomial difference. And if you look at all these different kinds of computers that I mentioned, and of course many others possibilities that I didn't mention, you'll also find that they differ by polynomial factors. That if you want to run a computation that takes t steps on one of them, it'll take t to some power steps on another.
Usually it's just only a constant.
Frequently it's only a constant. But of course this is an example where that's not the case. In any case, the main point here is that this is kind of the motivation of saying that the easy problems live in the complexity class P for polynomial time. If you try to fine-grain it more and say, oh, problems that take time n squared are easy, but problems that take time n cubed are hard, then you run afoul of this distinction between the different kinds of classical computers. Whereas because they have these polynomial relationships, the class P is robust, and it applies to all of these different things. Okay? And so this is a strengthening of the original result, and it's called the strong Church-Turing thesis, or, well, it goes by a variety of related names, which says that all physically plausible models of computation are equivalent up to polynomial factors. Okay? So now, of course, this is the point where physics starts to have a real input to the discussion. because physicists came up and said, well, we know this new other theory called quantum mechanics. And if we start to think about building a computer using quantum mechanics and having the bits actually be qubits and the gates be quantum gates, then it appears that this is not equivalent, not under polynomial time reductions, to these various classical models. And you know, further investigation, of course, we all know that that seems to be correct. We can't prove that it's correct, but it does seem to be correct. Okay, so this is a big contribution that physics has already made to computer science. It's shown that there's a major flaw with the strong Church-Turing thesis, and actually there are at least two kinds of computer science that we have to study. There's classical computer science and quantum computer science. Once you admit this possibility that there's two different classes, you have to worry, well, are there only two, or is it really a lot more? Maybe there's, quantum computers built from superconductors might be solving some totally different class of problems than quantum computers built from ion traps. And different architectures might give you different results as well. But as far as we can see, that's not the case. And in fact, that all quantum systems, that as far as we can tell, have the same quantum computational power, again up to polynomial factors. Okay? And so that's the quantum Church-Turing thesis. It generalizes the classical version to say, well, yes, there are some different complexity classes, different classes of computation models, but there's not very many. There's classical, there's quantum. We know of some kind of in-between ones, which you can think of frequently as just weakened versions of quantum mechanics. But as far as physics goes, I mean, it could be there's, quantum gravity computers might be stronger, but we don't really know that. We don't really know what the theory of quantum gravity is at this point. Okay, so one natural way one place you can go from here is to say, well, okay, so one of the motivations for thinking about quantum computers is the observation that quantum systems seem to be hard to simulate on a classical computer. So naturally, a quantum computer seems much better for that. And the fact that all of these different quantum systems have the same computational power suggests that that actually is a very good thing to do, that we could take some arbitrary quantum system and simulate it on a quantum computer and get out the answers we want. Right? Without the strong Church-Turing thesis, we couldn't say that necessarily, because it might be the system we want to simulate has some different computational ability than the one that we used to build our computer. But because they all seem to be the same, we can do this. And of course, the naive approach to this would be then to say, oh, well, so whatever properties of a quantum system we want to get out, we can just do the simulation and see what the answer is. So for instance, we could say what the ground state is. That's a very frequent thing that people want to do with quantum simulations. But here you have to be a bit cautious. Okay? So how will you actually run the quantum simulation that tells you these properties? Well, you'd set up some initial state. You'd run a quantum simulation that simulates the dynamical evolution under the Hamiltonian of this system. And then you'd make some measurement. It's basically an artificial experiment that you're simulating from start to finish. And the thing is that there's some physical systems where doing this will not actually tell you the ground state, because the system won't relax to the ground state in any reasonable amount of time. So these systems are called spin glasses. Let's see. So a spin glass is a type of spin system. So a spin system is a kind of simplified model where you have a bunch of particles. They're all fixed in location, but they have some internal degree of freedom, like a spin. Frequently, it's a finite dimensional thing. For our purposes, I guess I'm not content to think of it as a spin 1/2 particle, but it should definitely be, for everything I'm going to talk about on this talk, finite dimensional. So each particle has some finite set of states, but they're quantum states in general. And they're interacting frequently with some nearest neighbor interaction, but not necessarily. I'll be considering more general types of interactions. And so spin glasses were a type of spin system that was originally proposed to help understand structural glasses, like window glass. But they turn out to have their own kind of very complicated properties, and we don't really understand spin glasses either. And so it's kind of developed into its own separate field. Anyway, the thing about spin glasses is that when you try to cool them down to a very low temperature state, they don't cool down to your unique ground state. Instead, they get caught in local energy minima. They have very complicated energy landscapes with a lot of local minima, and frequently there can be big barriers, energy barriers, between these local minima, so that when it gets caught in one of them at a low temperature, it has a hard time getting out and jumping to another one. But even when it does jump to another one, there's so many of them that it's probably not the true global minimum, and so it'll stay in this new one for a long time. And the upshot is that it can take, in a big system, it'll take an extremely long time and effectively never relax to its true ground state or even its true thermal state. Okay, so that's the input of the physicist here. So an example of this would be a 3D Ising model. So this is just a classical spin system. You have a bunch of classical two-state particles arranged in a 3D lattice, and between each neighboring pair of particles you have a random interaction, which could be +1 or -1, ferromagnetic or antiferromagnetic. I guess those are opposite. Anyway, so once you think of this and think about the description of having this complicated energy landscape with a lot of local minimum, if you're a computer scientist, you'll recognize this type of structure as a structure that also appears in a lot of optimization problems. In particular, NP complete problems tend to have this structure, that there's some optimum, global optimum that you want to find, but there's a lot of local optima that are misleading, that locally, if you make only small changes in the solution, this solution seems to be the best. But globally, it's not the best. If you make changes to a lot of bits in the solution, you can potentially find a better one. And the reason these problems are frequently hard is because there's a lot of these false solutions, these local minima. And so that's exactly the same phenomenon that causes spin glasses to happen. So let's see. So NP, as we've heard, is roughly speaking the class of problems where it might be hard to find the answer, although not always. But if somebody tells you the answer, it's easy to check that it's a valid answer. So an example of this is satisfiability. You have some Boolean equation, a logical formula, and there's a bunch of different clauses. If somebody tells you, you have a bunch of variables which are true, false. So if somebody tells you an assignment of variables that satisfies this formula, it's easy to plug that in and check that it's true. But of course, if you're just given the formula, you don't know what to check. And if you have to check through all of them, that'll be exponentially many solutions to check. Okay, so so I mentioned that the reason that NP complete problems are hard is very similar to the reason that spin glasses are glassy. And you can make that even more precise by showing that certain types of spin glass Hamiltonians, finding the ground state energy is actually an NP complete problem. So in particular, so how do we prove NP completeness? Well, what we want to do is we want to take any problem in NP and write it as an example of this problem. So in particular, it's enough to take an NP complete problem like satisfiability and write it as an example of finding the ground state energy of a classical spin system. So how do we do that? Well, satisfiability has a bunch of different clauses, and we have to satisfy all of these clauses. So each clause is going to involve three variables. So it might be, not A, or not B, or not C. Okay, so one of them would have to be true. And what we can do is we can take a clause like that and convert it into a term in the Hamiltonian. Each variable, true-false variable, is going to become one particle, one two-state particle. And one of the states of those particles is called 0, might correspond to true, and the other state, 1, would correspond to false. Okay? And then given this clause in the Hamiltonian, given this clause in the satisfiability formula, we can turn it into a clause in the Hamiltonian that has high energy when the clause is false and low energy when the clause is true. Okay? And then the overall Hamiltonian is just going to be a sum of all these different terms that correspond to the different clauses in the satisfiability formula. And when the formula can be satisfied, that means that there's an arrangement of the particles, the spins, that gives 0 energy for every term in the Hamiltonian. Okay, so then in that case, the ground state energy of this Hamiltonian is 0. And when the formula cannot be satisfied, then that means that any way we assign variables, which means any way we arrange the spins, there's always going to be at least one clause that's not satisfied. And therefore, the ground state energy of this Hamiltonian has to be at least 1. It might be higher. Okay? So so this is a way we can convert any satisfiability formula into a Hamiltonian problem. And you see, using this conversion, if we had a way of efficiently solving this Hamiltonian problem of finding the ground state energy of any spin system in this class, then we could solve any satisfiability formula, right? Because we could say, well, okay, if somebody gives me a satisfiability formula, I'll convert it into a Hamiltonian problem and find its ground state energy. If the ground state energy is 0, I know the formula is satisfiable. If the ground state energy is higher than 0, I'll know it's not satisfiable. Okay? And since if you can solve NP, I mean, if you can solve satisfiability, you can solve any problem in NP. This means if you could solve this Hamiltonian problem, you could also solve any problem in NP. That's why it's NP complete. Okay, so so here we have this connection between finding the ground state energy of Hamiltonians and finding NP and solving NP complete problems. And that's not really a coincidence. The ground state energy of the Hamiltonian in general can be hard because the Hamiltonian might be the Hamiltonian for a spin glass that doesn't like to relax to its ground state. And they're not exactly the same thing, but they're closely connected. I mean, again, if you want to say something?
Do you mean NP hard here? I mean, because Hamiltonian is not even in NP, or we don't think.
Yeah. So yeah, depending how you define the problem exactly.
Yeah, fine.
Yeah. Right. So getting back to our original motivation of simulating a Hamiltonian with a quantum computer, or even just a classical computer, you'll see that the strong Turing thesis is playing a role here. In that, suppose we had a good quantum algorithm or a good classical algorithm for finding the ground state energy of Hamiltonian by cooling it. Right. That's a natural way to find the ground state of something. You simulate interacting the system with an environment and cool down the environment and wait for the system to cool down. And if it weren't a spin glass, you'd expect it to get to its ground state. And that would help you to find the ground state of the Hamiltonian. But we know that we can't find the ground states of Hamiltonians in general. So that's how we know from a computational complexity argument that some Hamiltonians have to be spin glasses. Okay? So I said that these things are not the same. So spin glasses won't cool to their ground state. That doesn't necessarily mean that a spin glass has to be computationally hard, right? On Monday, Eddie Farhi mentioned this problem XOR SAT, which seems to behave like a spin glass in practice. It doesn't cool to its ground state. But of course, there is a good algorithm to find the ground state. It's not very hard at all. And so that's an example of a problem which is a spin glass, but not computationally hard. The other
is nature solving such problems
like XOR SAT?
Yeah.
Well, XOR SAT doesn't have any geometric locality, so
right.
It's not something that kind of naturally appears.
Right,
but if you
problems that require linear algebra.
I'm not aware of them doing it, but I mean you'd have to look at specific examples. The main point I wanted to make here is that nature doesn't always do the best algorithm. Okay, that probably is not too controversial. But on the other hand, actually, sometimes it might be possible. I don't know of good concrete examples of this, but it might be possible for a problem to be computationally hard, but not be a spin glass. And the reason for that is that this business of finding the ground state, that's something that happens at 0 temperature. But most of the time, we're not interested in absolute 0 temperature. We're interested in some finite temperature, which for the computer sciences, that's physicist language for non-zero temperature. Finite meaning 1 over the temperature, I guess, is finite. So anyway,
what's temperature?
Yeah. So at finite temperature, not just the ground state should be populated at thermal equilibrium, but also some excited states. And it's possible that some of these computationally hard problems where it's computationally hard to find the ground state, might, once you start to populate the excited states a bit, if there's a lot of them, that might turn out to be more easy to do in some way. Okay, So now let's start to talk about quantum. So I talked already a bit about P and NP. But of course, if we want to talk about quantum problems and quantum Hamiltonians, we should start to think about quantum complexity classes as well. So BQP, you probably know, that's the quantum analog of NP, is the class of problems that can be solved in polynomial time on a quantum computer.
Quantum analog of P.
Quantum analog of P. Yes. QMA is the quantum analog of NP. That's the set of problems that can be checked in polynomial time on a quantum computer, although finding the answer might be hard. And so this is the relationships that we think these classes have. So P is certainly inside NP, because if you can find the answer yourself, well, you don't need to check it. You just don't. So that's straightforward. P is inside BQP because a quantum computer can simulate a classical computer, and all these things are inside QMA because QMA incorporates both classical checking and quantum algorithms. But we don't think that any two of them are the same, and we don't think that BQP is included in NP or vice versa. So John, I'm glad that you started to think about complexity classes, but proving that two complexity classes are not the same is only the first step. You also want to see what the other relationships between them are. And so, for instance, you might be very interested if there's a non-trivial intersection between these two classes. Okay, so QMA, well, QMA we've already seen a couple of times here, but let me just remind you that, again, it's the set of things you can check efficiently on a quantum computer. And so there's this little story with Merlin and Arthur. We've seen a lot of pictures of them this week, so these are mine. And so Arthur doesn't trust Merlin. Merlin, however, is very powerful. He can answer any question, so Arthur doesn't want to cut him out altogether. Arthur, on the other hand, is merely mortal. He can only do efficient computationally things. But in this case, maybe he's slightly more than mortal because he has access to a quantum computer. So he can do efficient quantum algorithms. And so whenever Merlin is trying to answer a question for Arthur, Arthur insists, because he doesn't trust Merlin, that Merlin provides some proof of the answer. And these QMA problems, like NP problems, have some sort of asymmetry. So Merlin only has to prove the yes answers. The no answers, Arthur is willing to let go, for whatever reason. And so an example of a problem in QMA is what's called the k-local Hamiltonian problem. So k-local Hamiltonian problem, you have a spin system that has a bunch of particles, and the Hamiltonian of this system is a sum of terms interacting k particles at a time. And so the local here refers to the fact that there's only k particles interacting at a time. It has nothing to do with geometry. So these k particles can be anywhere. They can be very far apart. And the question is, given some energy E and a k-local Hamiltonian, is the ground state energy of this Hamiltonian below E, that's the yes case, or is it above E plus delta? So we have to put this delta in because we don't expect to find energies to infinite precision. We have to put in some finite precision. Okay, and so this problem is in QMA. It's not too hard to see that. The way that that Merlin can prove the yes answer, the case where there's a ground state energy below E, is by giving Arthur a copy of the ground state. And then Arthur can plug that into his quantum computer and do some simulation of the Hamiltonian, which lets him calculate the energy. And then if the energy is low enough, it's below E, then he can see that. If it's above E plus delta, if the state that Merlin gave him has energy above E plus delta, Arthur will see that there's a problem, and he'll see that Merlin is lying. Okay. Of course, it could be that Merlin didn't give Arthur the true ground state, but if he gave him a state that's below energy E, then certainly the ground state has even lower energy. Okay? So I've shown that this problem is in QMA, but actually it turns out it's QMA complete. So that was shown by Kitaev. And so how would you prove that? Again, we have to show that given any problem in QMA, we can convert it into an example of this 5-local Hamiltonian problem. And so the way that works is, well, we're given this problem in QMA, and the only thing we know about it is that it's in QMA. Okay? And so what that means is that Merlin can present us a possible answer called a witness, and then Arthur has some quantum circuit he can run on this answer to check whether it's a valid witness or not. And so since this is the only thing we really know about this problem, we're going to have to use that and convert it into a Hamiltonian that has low energy when the witness is a yes instance, and when the instance is a yes instance, and a no answer if it's not. High energy if it's not. Okay, so what we do is we take this circuit and we imagine running it on a possible solution, a possible witness provided by Merlin. And then we'll run through the circuit and we'll get an output which could be yes or no. So if the state at time 0, the initial state of the circuit is phi 0, and then phi 1 at time 1, phi 2 at time 2, phi 3 at time 3, then what the way this proof works is that we can come up with a Hamiltonian, which is only interacting 5 qubits at a time, where the ground state is of this form, sum over t, phi t tensor t. So this second register is a new clock register that we've added on, and the first register just tells us the state of the circuit at different times. And you see that this ground state incorporates the whole history of this circuit. It's called the history state. And with appropriate Hamiltonian terms, we can make that any state that's not of this form have higher energy, and that any state of this form has low energy only if the output of the circuit is yes. Right? There's lots of different states of this form depending on what possible solution, what possible witness we put in here. Okay? And so if there's some witness that you can put in here that gives a yes output here, then this state will have low energy. And if anything you put in here will give a no answer, then this state will have high energy. Okay? And so the Hamiltonian that has this ground state constructed for this circuit will have low energy if and only if the original problem had the answer yes. Okay? So that's how we've done this reduction. We've converted the original QMA problem into an example of the 5 local Hamiltonian. And that's why it's QMA complete. Okay. So moving on. So why do we care about this sort of thing? Well, first of all, one thing we do care about definitely is simulating quantum systems. Right? We'd like to know properties like the ground state energy. And there's a lot of cases we actually can, on classical computer or maybe a quantum computer, find the ground state energy of a system. But understanding these hardness results tells us that we can't always do that. And understanding what kinds of problems are hard helps kind of block off and tell us where it's okay to look for better algorithms than we have now and where there's no hope. Okay? So if you think you come up with an algorithm that finds the ground state energy for any Hamiltonian, then you should probably check it. Because that would imply something, well, again, we can't prove that QMA is not equal to P or to BPP or BQP, but it's probably not the case. Okay, and I mentioned that spin glasses are not really that well understood, and that they have this relationship to computational complexity. So understanding the variety of Hamiltonians that can be spin glasses and be computationally complex might give us some insight on that. So techniques in this are useful in other areas. And of course, as frequently the case in computer science, once you prove hardness of one problem, you can use that to prove hardness of a bunch of other problems. Okay, so the natural question then is, which Hamiltonians are hard and which ones are easy? Some of them are certainly easy, and we know that some of them are certainly hard. But we'd like to understand which are which. But computer science teaches we have to be careful how we ask this question. We can't just say this Hamiltonian is hard, this Hamiltonian is easy. Just the same way you can't say, oh, this, I mean, people frequently do say, but it's sloppy language. This Boolean formula is hard, this Boolean formula is easy. Actually, you can only look at classes of problems. Any given problem, it has an answer, yes or no. It's very easy to write a program that outputs that answer, right, once you know it. It's just a fixed thing. So computational complexity is only defined on classes of problems, languages. And then we have to study how the difficulty of that problem scales with the size of the problem. Okay?
This guy on the left doesn't argue with the guy on the right.
It's a conversation, not an argument. It's I wrote it in Canada, where people get along much better. For Israel, I agree there should be more argument. But in the interest of keeping things short, let's have them be friendly. So okay, so we have to talk about a class of Hamiltonians and study if that class is hard or if that class is easy. So let's do that. So let's first look at classical spin systems, and we know from the thing I showed you earlier that if we have spin systems interacting 3 bits that can be anywhere, that's 3 local Hamiltonian for classical spin systems, that's an NP complete problem, right? That's equivalent to satisfiability. And 2 satisfiability, so if you have clauses involving 3 variables, that's hard. But if you have clauses only involving 2 variables, that's easy. So somewhere in between here has to be the difference between the hard and the easy ones. So let's start to see. So 2 satisfiability, where you have to satisfy all the clauses, that's easy. But if you have just kind of the Hamiltonian problem where you just want to find the ground state energy that allows frustrated terms, that's like max 2 sat, which is an NP complete problem. Okay? So it's okay if we allow 2 particle interactions that can be anywhere if we allow frustration. That's still hard. Okay, but these, from a physicist's point of view, these are very unsatisfying because, again, these particles are all over the place. Really, we're interested in cases where the particles are interacting over relatively short distances. So one example of that is if we have a 2D arrangement and we look at nearest neighbor interactions in 2 dimensions. So from a computer science point of view, that's a tiling problem. From a physics point of view, that's a 2 local Hamiltonian problem with nearest neighbor interactions in 2 dimensions. And this turns out to be hard, NP complete. Okay, but if we go to 1D and have nearest neighbor interactions in 1D, then it's easy. And this, I should say, is true even if you're not restricted just to bits, if each particle can have multiple states. Okay? Okay, so this seems like a pretty good picture. It says in 1D is easy, 2D is hard. But these 2D problems are still kind of unsatisfying from a physics perspective. Because in order to look at this, to make the hard constructions, you have to have an interaction here that's different from the interaction here, and that's different from the interaction here. And every nearest neighbor interaction could be totally different. I mean, totally different is an exaggeration. There's only so many things you can do with pairs of finite dimensional classical particles. But in any case, the structure of these things, they differ from place to place. And physicists are kind of okay with that so long as they're random. But these are not random. These are very structured, but in a complicated, unpredictable way. So that's pretty unsatisfying. So what physicists frequently like to deal with, other than random Hamiltonians, is translationally invariant Hamiltonians. So you'll have the same interaction at every place. Okay? And so that seems, from a physics point of view, much more natural to look at. So let's look at the 2D Hamiltonians with nearest neighbor translationally invariant interactions. So this turns out to be hard as well. So this is not NP complete. This is next complete. Next, I'll explain in a minute and why I had to make this difference. So it's kind of a technical difference between these two, but morally it's basically the same result, that this is hard. Yeah. Next slide. Okay. On the other hand, if we go to 1D translationally invariant Hamiltonians, well, we know it should be easy, but it turns out that it's actually very easy. So whereas this non-translationally invariant takes a time that's polynomial in the number of particles, the translationally invariant one takes I don't know. It might be. The translationally invariant version takes a time that's polynomial in the log of the number of particles. And I can tell you this is definitely not log time complete. Not. It's even easier than that. Okay. So these two are kind of about the same hardness, that going from 2D without translation invariant to 2D translation invariant, they're about the same, but in 1D translation invariance actually makes it easier. Okay, so what's this business about next? So next is non-deterministic exponential time. So it's like NP, but it takes exponential time to check the answer. Okay, so why is that? And why do we need that? And the reason is that in the translationally invariant problem, the term, the nearest neighbor term, the Hamiltonian that's interacting nearest neighbors, is the same from place to place. So the only input we have in the problem is how big it is. It's an n by n system, okay? And the number of bits it takes to specify n is only log n, okay? So before we were talking about something that took a time that's polynomial in n to check. Now we're taking it to something that's still polynomial in n, but that means it's exponential in log n, okay? And so that's why we have to talk about next complete instead of NP complete. And so even though next is a much bigger and much harder complexity class, because we've shrunk the encoding to log size, the input to log size, the difficulty is very comparable. Okay? Yeah. Yeah, so the specification of the Hamiltonian is, you can think of it as just a fixed parameter. And in fact, what's going to happen is you can think of a separate language for each Hamiltonian term, right? Because it's just fixed, okay? It's just some constant thing. So you can think of it as part of the input if you like, but it doesn't vary. It doesn't change size. Or you can fix it and just say, let's look at the language of different sizes for this particular term. Okay? Okay, so now let's talk about quantum quickly. So quantum, I told you that 5 local Hamiltonians are QMA complete. And Umek mentioned that in 1D, if the system has a spectral gap, we now know that that's easy. That's polynomial time. So again, let's try to fill this in and see where the border is between hard and easy. So 2 local Hamiltonians. So if you have 2 qubit interactions, that's hard. If you go to 2D, nearest neighbor interactions between qubits, that's still hard, QMA complete. That's not too surprising, thinking of the classical analogy. But it turns out that if you go to 1D and look at nearest neighbor interactions, non-translation invariant, that's still QMA complete. So that's a difference from the classical case. Now to do this, we have to go to bigger particles. I think the record right now is 8 state particles for this. And for qubits or smaller particles, we don't know what the answer is. So that's one possible borderline between the hard and the easy case. But we can also ask the same question as we did in 2D. What happens if we look at translationally invariant problems? So translationally invariant 1D Hamiltonians are still hard. So again, we have this problem with the encoding. So we have to go from QMA to QMAX. It's kind of the same relationship. And so these translation invariant Hamiltonians are QMAX complete. And we can even add an additional symmetry and say, let's furthermore have reflection invariance. So the interaction between left and right is the same as the interaction between right and left particles. And in that case, it's still hard. And so you notice there's not really much space between these. Okay? We've added basically as much symmetry as we can to the system. You might expect symmetry is going to make it easier. And in the classical case, it does in some cases. But in the quantum case, it doesn't really. So one side note. You remember in the 1D case, classical case, translation invariance made the problem easy. It's polynomial as a function of log n. Whereas here, it's still QMAX complete. So the difference between polynomial and QMAX is so big that we can actually prove that they're different, which for a computational complexity is really rare. So we can actually prove that the 1D translational invariant Hamiltonians are harder than 1D classical translation invariant Hamiltonians. That P and QMAX. They have to be pretty far separated for us to be able to prove it. But the difference is so big in this case that we can do that. Okay, so I'm really running out of time now. But so QMAX, remember, it's same. Yeah. So this we're comparing the right way because this is QMAX. The other one is P. So both of these are P and QMAX as a function of log n. So we're comparing on an equal basis. So this is even if it's not translationally invariant. Yeah, probably not actually. So, or at least that's not known. That one's not known. No. It's not between this and this. It's between the classical translational invariant Hamiltonians in 1D and the quantum translationally invariant Hamiltonians in 1D. That's the provable difference.
So for the quantum, the translationally invariant doesn't.
That's right. It doesn't help you, except maybe at fixed particle size. We don't know about that. Yeah. Yeah, that's a very good question. That's a very good question, and I don't know the answer to that. I'd like to, but I don't know the answer.
So I actually defined QMAX once just to prove a lower bound for it.
Okay.
It doesn't have poly-sized quantum circuits. It's quantumly sized. Some fantasy that it's actually been used for something.
Right. Right. Okay. So anyway, one thing you might have noticed in my exchange with Patrick is that I said that we didn't have to include the specification of the Hamiltonian as part of the input to the problem. We could say, here's a specific Hamiltonian term, and we're just going to study the complexity as a function of the size of the system. And so, whereas before I said we had to consider classes of Hamiltonians and study the complexity of them, actually that's not completely true. With translational invariance, we can study a single Hamiltonian term and study its complexity. And there's still a class there, which is how big the system is. But that's kind of liberating, right? Because that tells us that the kind of the natural thing to think about is the Hamiltonian term. And now we can say, is this Hamiltonian term hard or easy? Well, we can ask the question. I don't know how to answer it in general. But it points to an interesting thing to look at. And so Dorit told me that as the last talk, I should try to be either entertaining or provocative. I figured it'd be easier to be provocative. So now we're starting the speculation part of the talk, which will only be a few slides. Oh, thank you. And also I know that the best way to be entertaining is to be provocative. Okay, so speculation. So this same idea of, well, let's look at a fixed rule set and only study the class as we vary the size of the problem. This is something that could apply to a lot of other computer science type problems. But it's been done before, but somehow it never entered the standard repertoire of complexity theory. And I think it should, because there's a lot of interesting problems that could potentially benefit from it. So for example, Go is a game. The standard version of it is played on a 19 by 19 board, but the rules generalize easily to boards of other size. And so there's a standard result that says that Go is a piece-space complete problem. But the problem that they prove is piece-space complete is, well, we're given a Go board, and there's a bunch of pieces already on it. And given this position, who can win, black or white? Okay, but that's not the real Go problem. The real problem for Go is we start with an empty board, or maybe a board with some standard handicap. And given that, who will win, black or white? Okay, that's really the more interesting problem, because the configurations that appear in this piece-space completeness proof, they might be totally artificial ones that would never appear in a real game. No, that's true. That's true. But partly that's because the problem from the empty initial state, that's way too hard for them. But again, the end. I mean, so my understanding is that using this piece-space completeness result, you can generate endgame situations which will completely stump Go masters because they're so weird that they're different from what they're used to. So that's an indication that the hardness is maybe not representing the real game. Or maybe it is, and just, even Go masters are not good enough to fully get the complexity of the game. Anyway, my point is simply this, that if you really want to study the complexity of Go, maybe the way to think about it is in terms of this same procedure, where we study a fixed rule set and then just vary the size of the board. And I mean, I don't know what the answer to that is, of course. I have no real way how to prove it. But just the way that the other version of the problem was piece-space complete, where it was the kind of the non-translationally invariant Go, the correct version maybe should be X-space complete. It's a reasonable thing to guess. No, probably not.
This looks much harder.
Yeah, probably.
Right. Well, I mean, it's worth saying that for the other results, right, that, as I remember, the way that you prove it is to sort of design a Turing machine that first finds the size of the board and then uses that as an input and then runs the Turing machine. So
Yeah.
that,
For the tiling problems,
Yeah, right, for the tiling thing. So now, you know, in order to do that with some game which is just given to you, like Go, and you don't get to engineer, it seems like really, really hard undertaking. So I guess this is the provocative part of the
Yeah,
talk.
that's right. This is speculation.
Yeah. Oh, okay.
Well, yeah, to get started, you might want to do that. Well, no, not really, because it doesn't have the right structure. I mean, this alternating quantifiers is not the same as a Hamiltonian. Yeah, okay. So that was what physicists can offer to computer scientists. So now here, let's see what computer scientists can offer to physicists in terms of speculation. So again, if you look at these hardness proofs, they basically work by simulating some sort of Turing machine using the tiling rules, the Hamiltonian terms, whatever. Another way to do it would be to simulate a cellular automaton. And we know from computer science studies that even very simple cellular automaton can be universal. They can kind of calculate anything. And partly motivated by that, and partly just kind of thinking about how you'd try to solve these problems, it seems to me that it's likely that even some very simple Hamiltonians, at least in 2D, maybe not in 1D, but at least in 2D, some very simple Hamiltonians with low-dimensional particles could very easily be computationally hard. Again, I have no idea how to prove that. You don't have quite as much ability to kind of write down the right rules that you want, but this is speculation. And the thing is that not only can very simple systems be hard, but computational universality is actually very common once you start to look at rules of sufficient complexity. Okay, and in some sense, it could even be generic. So this is what the computer scientists can offer the physicists: the suggestion that computationally complex problems, and therefore spin glasses, might be kind of generic among Hamiltonians of sufficient complexity. And if that's the case, you have to ask, well, where are they? I mean, physicists do study spin glasses, but they don't usually study translationally invariant spin glasses. I don't think there was an appreciation that could even exist. But more than that, most of the problems that theoretical physicists at least like to study have very kind of regular ground states in some way. They might be, exotic, but they're not going to be computationally hard to find. So my suggestion is that maybe if we look to just slightly more complicated systems, we'll start seeing these things. And theoretical physicists have been blind to them because, we really like the simple systems. They're much easier to work with. But of course, the real world is not so simple. It has all sorts of defects and, imperfections and impurities and stuff like that. And maybe the reason they're there is not, some accident of history. It's an inevitable part of history, because finding the true ground state of the universe, that could be a computationally hard problem. So let me stop there. Thanks.
Questions?
Thank you. So you had this slide where you were listing all the different quantum Hamiltonians. And my question is, putting in numbers, not going to taking the n to the infinity, starting from how many qubits in every case, I guess, that would be a classically difficult problem for a state-of-the-art classical computer.
Okay. Don't know enough about for I don't know, maybe like 30, 40 qubits. predict which
So do you expect that these things will be easier if you have a finite temperature in different states? And then you only have to get to an ensemble. You don't have to get to the ground state. But basically, also has huge implications of how can we interpret an experiment.
Question: is there a PCP translation? Is there a translation invariant PCP theorem in the class?
doesn't work.
No, but use an expander graph. Use an expander graph, but make.
So you want to use it. You want to use one.
Cayley graph or something like that. Instead of do it for whatever.
Yeah, it means the interaction is kind of universal, right? You can, by looking at the right size, you kind of simulate every other interaction. How do you tell what itself a hard problem?
Last question. Actually, it was. I just wanted to make a comment which occurred to me as you were saying all this, which is it's something very nice about our community, the quantum computing community, which is it occurred to me as you were saying it that every time you talked about what physicists teach us and computer scientists teach us, what you were really saying some of the time was what physics teaches us and what computer science teaches us, because it was in fact people from the other side who made those contributions, which is a great thing for a center like this.
Okay, let's get.